Now that we've spent a fair amount of time looking at how we can use circles to measure angles, we're going to use that understanding to see how we can extend trigonometric functions to what are called circular functions. First thing we're going to do is discuss how we can use circles to define trigonometric functions. Then we're going to define the sine and cosine functions not just on right triangles but on circles. We're going to do an example problem, and then we're going to define the other circular functions in a very similar way as we do sine and cosine. All right, so let's remember how we use circles to define angles. So we start off with a unit circle, or actually it doesn't have to be a unit circle. It could be a circle of any size. And what we do is we draw a line from the origin to the circle so that we make the angle theta that we're looking for. Now what we're going to do is use circles and this way of measuring angles to extend trigonometric functions to circular functions. So first thing I want to ask is, well, I don't see any right triangles. Is there a right triangle in this picture? And the answer is, yeah, there's one right there. If we go to the point where the line and the circle intersect, drop a vertical line down to the x-axis, that makes a nice little right triangle. The question is, what does the point on the circle have something to do with the trigonometry of that right triangle? Well, okay, so the point has some x-coordinate x and it has some y-coordinate y. Can we find that anywhere on the right triangle? Well, you bet. That horizontal distance between the origin and the edge of the triangle, that's the distance x. And the vertical distance between where the x ends and where the xy point is, that has distance y. And then, well, the hypotenuse has length of the radius of the circle, whatever that is. Now, you can make the radius whatever we want, and I will tell you right now that in different problems, you will want different radius measures, radius values. But in this one, we're to make it a little easier, we're just going to use a unit circle, which means our radius is going to equal 1. So now if we want to define sine theta, that's actually pretty easy to see, right? You just take your opposite over your hypotenuse, your opposite being y, your hypotenuse being 1, and that's just equal to y. So on a unit circle, the y-coordinate is literally the sine of the angle. And if you want to find, and there's sine of the angle right there. Now, if you want to find the cosine of the angle, you just take the adjacent side, which is x, you take the hypotenuse, divide that, and get 1. X divided by 1 gives you x, which means that the x-coordinate is the cosine of the angle. So the x and y coordinates are very much related to the trigonometry. In particular, they are the sine and cosine. Now that is not literally going to be true if you have a circle that has radius that is not 1. But if the circle is radius 1, this is a nice convenient way of looking at sine and cosine. And we can use a similar process for the other trigonometric functions. As long as we know which sides you're dividing on the other trigonometric functions, you can figure out how the x and y coordinates factor into those. And we'll do that at the end of this video. All right, so one of the things that this circle definition of sine and cosine allows us to do is it allows us to do trigonometry that's not just between 0 and 90 degrees. One of our constraints of having a right triangle is the smallest the angle can be is 0, and actually can't even be 0 really, because with an angle of 0, it's not a triangle. And the biggest the angle can be is 90 degrees, and it can't really even be 90 degrees, because if you try to make a triangle with two 90-degree angles, it's impossible to do. So if we're working with circles, we can actually extend our trigonometric functions beyond 0 and 90 degrees, and let's see if we can figure out how. So here's an angle that extends past 90 degrees, right? Now, again, and we're using a unit circle just to illustrate what's going on. We can still define cosine theta equal to x. That's all it was when we were between 0 and 90 degrees. We saw it in the previous slide. We can still define cosine theta to be x and the sine theta to be y. And we can even draw a right triangle to illustrate how the x and y work together by doing the same thing, taking the point and dropping a vertical line segment down to the x-axis. And even now, and there's our x-coordinate and our y-coordinate, and even there we can look at what the adjacent and opposite sides and the hypotenuse, how those interact to do our trigonometric functions. It's going to be a little sticky though, because sometimes our x and our y can now take on negative values. And we'll see how that works in our example. So here's our example. We're going to look at sine of 150 degrees and cosine of 150 degrees. All right, so there's our angle. And we're going to make a right triangle. And there's our right triangle. I'm gonna wait to choose the radius of my circle because I'm gonna want to do it in a very convenient way later on. So I'm not gonna choose the radius of my circle. It's not gonna be a unit circle. I'm gonna choose one that's more convenient. So if you see that small angle in the right triangle, we can actually figure out what that angle is, because if you add that small angle plus the 150 degrees that it takes to get to that line, to get to the hypotenuse, that is going to add up to 180 degrees, because the positive x-axis, negative x-axis are at an angle of 180 degrees. And so that means that angle has to be 30 degrees, because 150 plus 30 equals 180. And the nice thing about that right triangle that I'm looking at is that is a 30, 60, 90 right triangle. And we understand very well what a 30, 60, 90 triangle looks like, what the sides of that triangle are going to be. So again, I'm going to try to choose a convenient size of the triangle. So I'm going to do one where the hypotenuse is 2. That means the short side of that right triangle is going to be 1, half of that. And then the longer side, that's not the hypotenuse, is going to have length square root of 3. Now you notice I didn't just put square root of 3 there. I put negative square root of 3. And that is because my x-coordinate, since I'm on the left side of the origin, that x-coordinate is going to be negative. So instead of being square root of 3, it's got the same length. It's just going to be negative square root of 3 because we're looking not just at the length, but at the actual x-coordinate. So now the right triangle is all set up. I know the x-coordinate, I know the y-coordinate, I know how to set things up. So if I want to figure out sine of 150 degrees, I just take the opposite side, which is 1, that's my y-coordinate, divided by my hypotenuse, which is 2, and get 1/2. If I want to find the cosine of 150 degrees, this one's kind of a trip. You're going to take the adjacent side, but the adjacent side isn't going to be square root of 3. It's actually going to be negative square root of 3 because that's the x-coordinate. And then you're going to divide that by the hypotenuse, which is 2. And if we want to clean that up a bit, we get negative square root of 3 over 2. So we actually get a negative value for cosine of 150 degrees. All right. So now let's do another problem with a mystery angle t. And this is an angle t that we're actually never going to be able to compute, but hopefully we'll be able to figure some stuff out. So here are our clues about t. We know that t is between 180 degrees and 360 degrees. And we know that the cosine of t is equal to 2/7. Question is, what is sine of t? All right, we're going to see if we can figure that out. So here's our right triangle, or not a right triangle. Here's our circle. And again, we're gonna wait to figure out how big the circle is until we find a radius that's convenient for us. The first thing is, where do I even draw where that angle is going to be, where the angle t is going to be? Well, here's the deal. I know that cosine of t is positive, first. Second, I know that the cosine of t is determined by the adjacent side, right? The adjacent side being x divided by the hypotenuse, which means if cosine of t is positive, that must mean my x-coordinate is positive as well. And where is my x-coordinate positive? Well, in those two places where my asterisks are, right? In the quadrant 1 and quadrant 4. The other two quadrants are places where my x-coordinate is negative. So in order for cosine of t to be positive, I need to be in one of those two quadrants. That's not so bad. I also know that t is between 180 degrees and 360 degrees, which means that I can't be in quadrant 1 because that's between 0 and 180 degrees. So I'm going to take that one out. And so now I'm going to go ahead and draw my right triangle. So here's my right triangle. Now I want to be very careful about how I choose my radius, because again, I can choose that circle to be as big or as small as I want. Well, if you look at the cosine of the cosine of the angle is 2/7. The cosine of the angle is also my x-coordinate divided by my hypotenuse. And so if I want to make that as convenient as possible, I want to make my x-coordinate equal to the 2 and my y-coordinate equal to 7, because then when I divide 2 by 7, I get 2/7. So that's what I'm going to do. You see how that works? So that 2 is my adjacent, that 7 is my hypotenuse. When I divide those two to get my cosine, I get 2/7. That's exactly the type of triangle that I want. I don't have any fractions. Everything is nice. So now I need to find what sine of t is. And in order to find out what sine of t is, I need to know what the opposite side is. In other words, what is the y-coordinate? So I'm going to give that a name, a y. I don't know what it is yet. Hopefully I'll be able to figure it out later. So the question now is, once I figure out y, I've got the problem done. The question is, how do I actually figure out y? Well, fortunately, the Pythagorean theorem is going to help us out. Because what the Pythagorean theorem says is that 2 squared plus y squared equals 7 squared, right? The two sides squared and added together equal the hypotenuse squared. And that gives me an equation where I can solve for y. So 2 squared is 4, 7 squared is 49, and when I solve for y squared, I get 45. And then when I solve for y, oh geez, do I get square root of 45? Actually, it turns out no. And if you look at the triangle for a little bit, it's not going to be too hard to, it's easy to overlook, but it's not too hard to figure out why. Notice that that y-coordinate is below the x-axis. That means that the y-coordinate is negative. So it can't be positive square root of 45. It has to be negative square root of 45. So that was kind of tricky. All right, so there's my negative square root of 45. And now finding the sine of t is pretty straightforward. You just take your opposite, divide it by your hypotenuse, and we end up with negative square root of 45 over 7. All right, so, and as I mentioned before, you can use the exact same techniques to define the other circular functions in the same way. All the extensions of the trigonometric functions that we did back in section 4.1. So here's our triangle again, right triangle. This time I drew it in the first quadrant, but it works in any quadrant. If I want to find sine of theta, that is opposite over hypotenuse, which is y. Cosine of theta equals adjacent over hypotenuse, which is x. And notice that I'm using a unit circle again. That's just to make things a little bit easier for these particular functions. But again, these work for any size circle that you want. If I want to find tangent of theta, well, that's an interesting one. Tangent of theta is the opposite over the adjacent. The opposite is y. The adjacent is x. And not only that, but we know what y is. If you look a line above, y is equal to sine of theta. X is equal to cosine of theta, which means that tangent of theta is equal to sine theta over cosine theta. Which means I don't even have to know what x and y are. As long as I know what sine theta and cosine theta are, I can figure out tangent of theta. But in any case, cotangent of theta, same deal. That is adjacent over opposite, so that's x over y. Now remember, my x is cosine of theta, my y is sine theta, and so that means it's also cosine theta over sine theta. And then my secant theta, that was hypotenuse over adjacent, so that's 1 over x. And remember, x is cosine theta, so that actually gives me 1 over cosine theta. And then finally, cosecant of theta, that is hypotenuse over opposite, that's 1 over y. Y, remember, is sine theta, and so we get 1 over sine theta. So these are different ways of looking at the other circular functions using the unit circle. All right, so I've got 2 sets of activities for you to work on that go with this video. One is called circular functions, and the other one is called more circular function problems, in case you didn't get enough from the first one.